Hello everyone. Let's start off with a few questions, shall we? Why would you think that certain waves appear to be positive in one lead while appearing negative in another lead? We all know that depolarization and repolarization are opposite phenomenon. Why then would QRS and T waves usually be in the same direction? What wave represents sinus node depolarization? Go ahead and pause the video and think about an answer. Let's start off with a few basics. Most cells in the body are negative on the inside and positive on the outside. Now, the heart cells can take up one of three distinct roles. The first one is that of a pacemaker. So these cells have a unique capability. What they can do is they can spontaneously flip the charges so they become positive on the inside. So the process wherein the cells are negative initially to begin with and then turn positive on the inside is called depolarization. And depolarization, like laughter, is contagious. So, in essence, the pacemaker cells start off an impulse by spontaneously depolarizing, and this impulse is then passed on to specialized conducting cells. When a certain cell depolarizes, the cell next to it also would want to depolarize. So, the depolarization wave jumps from cell to cell, and thereby the impulse that's starting off in the pacemaker rapidly goes through the different conducting cells in the heart. And from here, it would end up going to the myocytes, the muscular cells of the heart. And when the impulse reaches the myocytes, the muscles of the heart contract. So the three distinct roles, the pacemaker is really good at rapidly initiating impulses, and also it does this process regularly. Now, once the impulse has originated, it goes on to the conducting cells, and the conducting cells are extremely efficient with passing on the impulse to the other cells. And lastly, when the impulse reaches the myocytes by a process called excitation contraction coupling, these cells contract. Now, for some reason, on a bad day, if the pacemaker cells do not function, some of the other cells might take up the role of a pacemaker, but they may not be as fast or as regular. Similarly, if something is wrong with the conducting cells of the heart, the myocytes can actually conduct the impulses also, but then they just won't be as efficient. So it just takes longer for the impulse to be conducted. Now, once the process of depolarization is complete, eventually the cells return back to being negative on the inside. And this process would be repolarization. So notice how depolarization and repolarization are opposite phenomenon, and the pacemaker cells go through these cycles repeatedly. Now that we've understood the basics of depolarization and repolarization, let's see how all this pans out in the heart. As we all know, the heart has four chambers, so you have the right atrium, the left atrium, you have the right ventricle, and the left ventricle. The impulse starts off in the pacemaker's side, the SA node, in a normal heart. And from here, it splits through the right atrium, and then it eventually goes on to the left atrium. And it also reaches the junction between the atria and the ventricles, the AV node. And here there is a significant slowdown in the speed at which the electricity is conducted. This is important because this gives the time for the atria to contract and pump blood into the ventricles. Now, at this point, the impulse eventually gets passed on to the bundle of His, which pretty quickly splits into a right bundle branch and a left bundle branch. And the left bundle branch pretty quickly splits into a septal fasciculus, an anterior fasciculus, and a posterior fasciculus. And these branches, through much smaller branches called Purkinje fibers, transmit the impulse to the myocytes, which then contract and pump blood. So, as we've talked about, electricity in the heart follows a very predictable pattern. Now, if there were a magical way in which we could visualize any changes in this flow of electricity, we might be able to pinpoint if there is any problem underlying the whole system. So, for instance, if the pacemaker isn't functioning, or if the conduction isn't happening the way you would predict it to be or want it to be, you could extrapolate that information into maybe there's something wrong with the heart that's causing this disruption in its normal function. If there were a magical way in which, most of us could actually see the flow of electricity in the heart, that would be awesome. The problem is doing it at scale where every physician can do it can often be very difficult. So, an alternative would be taking these signals that are passing through the heart and transcribing them onto a piece of paper so you can actually see the flow of electricity. And let's explore how that's done. So we've said that we're trying to get whatever is happening in the heart onto a piece of paper. And if you think about it, there are really three things that you want to figure out in terms of the flow of electricity. The first one is which way is the direction of depolarization or repolarization. The second thing that you would try and define is how intense is this wave of depolarization or repolarization. And the third thing is how do these waves change over time? To figure this out, we follow a specific convention. So let's say you have a wave of depolarization going from left to the right in the heart. The convention we follow is that if you have a positive electrode and the wave of depolarization is going towards it, you would notice a positive deflection. Now, if this wave is really strong, the magnitude of the positive deflection would be higher. In a similar fashion, if you have a wave of depolarization flowing away from the positive electrode, you would have a negative wave. And if the strength of the impulse going away is really strong, the negative amplitude of the wave would be higher. So let's consider what happens when you have three positive electrodes all located in distinct locations, and you have a wave of depolarization going from the left to the right. Now, when you look at this lead, the wave is flowing towards the lead, and so you would have a positive deflection. If you look at this lead, it's flowing away from this lead, and so you would have a negative deflection. How about this one? Notice how the flow is pretty much perpendicular to the third lead. So initially, it seems like it's approaching the lead, and so you would have a positive deflection. When it's right in the middle, it returns to the baseline. And then when it recedes from the lead, you would see a negative deflection. And once the flow is complete, it would return back to baseline. So in essence, you're seeing a biphasic pattern. Now, we talked about earlier that depolarization and repolarization are opposite phenomenon. So let's say there's a wave of repolarization now going this way. Which way do you think the leads would record the impulse? Well, this specific lead would now have a negative wave because it's a wave of repolarization, and that's the opposite of depolarization. This lead would have a positive deflection, and this lead would record a negative wave followed by a positive wave. So this would be repolarization, and this would be depolarization. All right, very good. Now let's play along with the information that we've just learned. So we still have our three leads, and we already said that if a wave of depolarization goes this way, you have a positive wave, you have a biphasic wave, and you have a negative wave. Now, what if you had an impulse that's going like so? Notice how the general direction of this wave is still towards this electrode. So you would still have a positive deflection, but then it's not quite going straight at it, and so the amplitude of the positive wave would be slightly lower. On the other hand, when you look at this electrode, so let's just call them electrode A, B, and C. So if you look at electrode B for this wave, you would notice a negative deflection, but it's not quite as intense. And lastly, if you look at lead C, notice that it's still perpendicular to lead C, and you would still follow this pattern. So in other words, if you have a perpendicular electrode and the current's going like so, or like so, or like so, all three would essentially generate an impulse that looks like that. So notice how we're able to define the direction of the electric flow as well as the intensity of the electricity flowing by looking at the wave that's being produced. Now let's take this a step further. What if you have two leads? So you have a negative lead and a positive lead. And essentially, the two leads are going to give you a measurement that's going to help you extrapolate the flow of depolarization from the negative to the positive lead. So let's consider the first scenario. You have a flow of current that's going like so. If that's the flow of current, you would pretty much just see a positive deflection. How about if the flow were like so? Now, if you remember your physics and vectors, you could split this, you can split this flow of electricity into two directions, right? You have a component that goes like so, and you have a component that goes like so. So notice how there is a component that's flowing towards the positive electrode, and so you would still have a positive deflection, maybe not as big as this one, but it's still going to be positive. Now, what if the flow of electricity is like so? If you think about it, again, you can split the vector into this and this. Notice how there's nothing flowing towards the positive electrode, and so this one would actually register a negative wave. And lastly, if you have a flow of current that's exactly perpendicular to the negative and positive electrodes, you would register a biphasic wave for the reasons we've discussed earlier. So based on the intensity of the wave, as well as whether it's positive or negative, you can pretty much figure out which way electricity is flowing. Now that we have a good basic understanding of how leads work, let's think about how we can structure a system to best understand the direction of flow of electricity. If you think about it, for you to be able to define the exact direction of current flow, you would have to measure the current flow in at least three different dimensions, right? You would want to see whether the electricity is flowing from left to right or right to left. You would want to see if it's going from up down or down up. And you would also want to see if it's going from the front to the back or back to the front. So the way we accomplish this is by placing multiple different leads over the body. So let's go ahead and draw out arms and body of what looks like a human being. I hope. Well, I guess that's a good enough human being for this purpose. So let's start off with having leads placed on the arms and legs. Now, understand that these leads should be placed symmetrically in both the arms and the legs. And the one on the right arm, we'll call it RA, LA for the left arm, LL for the left leg, and RL for the right leg. Now, the right leg is the neutral lead. So what this does is it looks at any background noise, things that are of no relevance, and tries to eliminate them from the EKG, while the other leads kind of help us see which way electricity is flowing. Now, the convention the machine follows, so we don't have to do anything other than putting it on the person's body, and the machine kind of interprets the leads as being either negative or positive based on the specific scenario. So the right arm, the machine considers is always negative for the present purpose. The left leg is considered to be always positive, and the left arm takes the opposite role. So essentially, relative to the right arm, it would become positive, and relative to the left leg, it's going to become negative. So if you connect these, so essentially, if you were to connect the right arm and the left arm, you would have a direction that looks like so, and this would be lead 1. Now, if you were to connect the left arm and the left leg, you would have something that looks like so, and if you were to connect the right arm, you would have something that looks like so. So essentially, the right arm and left leg would be lead 2, and left arm and left leg would be lead 3. So, in essence, if you were to just extrapolate it to the side, you have lead 1, you have lead 2 at approximately 60 degrees. So, this would be 60 degrees. And then you would have lead 3. And this would be at 60 degrees. So, the total would be 120 degrees. Now, in essence, you have the negative and positive set like so. And by looking at a specific wave in terms of how they show up in these leads, you can interpret which way the specific wave is going as well as how strong it is. You could take RA and LL, average them out, and make them negative relative to LA, and then you would have a current that looks like so. So let's go ahead and change the color. And this would be augmented VL. Similarly, you can take the LA and LL, average them out, and make them both negative relative to RA, and then you would have AVR. And lastly, you can take RA and LA and average them out and make them negative. And if LL is positive, you would have AVF. So if you were to draw those here, you have AVL, which is negative 30 degrees. You have AVR, which is a total of 150 degrees negative. And lastly, you have AVF, which is at 90 degrees. So, in essence, what these leads are doing is trying to provide you a good understanding of whether electricity is going from the left to the right or right to the left. And they're also telling you if electricity is going from the top down or from down up. Now, we would also want to know if electricity is going from the back to the front or front to the back, and you accomplish that by placing precordial leads. So you have 6 precordial leads generally, The first one is placed just right of the sternum in the fourth intercostal space, so that would be V1. The second one, V2, is placed in the fourth intercostal space to the left of the sternum. V4 is placed in the midclavicular line in the fifth intercostal space, and V6 is placed in the fifth intercostal space in the mid-axillary line. Where are V3 and V4? Well, V3 is between V2 and V4, and V5 is between V4 and V6. So now let's take these and look at what exactly they can tell us about the heart. So you have the heart right here. So if you were to take that, let's look at the direction of all the vectors. So you have lead 1 going like so, lead 2 going like so, you have lead 3 going like so, and then you have the augmented limb leads. So you have AVL, AVF, and AVR. So if you think about it, 1 and AVL are best looking at the left side of the heart. So they're both pointing towards the left, and these would be lateral leads. 2, 3, and AVF are best looking top down, and these would be the inferior leads. Notice how AVR is all by itself, and you can pretty much call it anything you want. So you also have V1 and V2, the first two precordial leads, and these give you an excellent look from the front of the heart. So these would be anteroseptal leads. So V1 and V2 are the anteroseptal leads. Then you have V3 and V4, which give you a very good look at the anterior part of the heart, and these would be anteroapical leads. And lastly, you have V6 and V5. And if you think about these are being placed in the mid-axillary line and also between V4 and V6. So they're again lateral to the heart. So they're still giving you a view of the lateral side of the heart. And these are still the lateral leads. Now, one way to think about it, notice how 1 and AVL are pointing towards the upper lateral side, and V5 and V6 are pretty much pointing to the lateral side. So, if you think about it, 1 and AVL would be considered high lateral leads. So, now that we've talked about how depolarization and repolarization are recorded in the EKG, and also talked about how we place multiple leads on the body, let's go ahead and see how the waves are expected to look on an EKG. So let's go ahead and draw back all the axes. So you have 1, 2, 3, you have AVL, AVF, and AVR. And we also said that 1 is at 0 degrees, AVL is negative 30 degrees, AVF is 90 degrees, AVR is negative 150 degrees, lead 2 is 60 degrees, and lead 3 is 120 degrees. We've also talked about the conduction system of the heart. So we have the atria, in the ventricles. You have the SA node connected to the AV node, and from there you have the bundle of His, the right bundle, and left bundle that pretty quickly breaks into a septal branch, an anterior fasciculus, and a posterior fasciculus. So one thing to see is once you have depolarization of the SA node, the wave of depolarization quickly spreads and it also goes to the AV node. So there are multiple waves of depolarization all going in different directions. So let's go ahead and draw the one to the AV node also. So you have the SA node and the AV node. So one thing to kind of think about is if you have so many different waves of depolarization at any given point of time, would you actually see every single wave of depolarization on the EKG? Let's consider the following example. Let's say you have the following vectors, and these are all facing rightward, and then let's say you have smaller vectors facing leftward. Now, there are multiple vectors all over, but then if you were to add them up, you would end up with only one vector that looks something like so. So if you were to have a negative electrode and a positive electrode, all this would be summed up into pretty much one wave that looks like that. So all these six vectors would transcribe into one positive deflection. Similarly, if you look at all the waves of depolarization in the atrium, all of them translate into one vector with a general direction about that. And the normal axis is typically between 0 and 75 degrees. So if you were to draw this wave, you would notice that because it's between 0 and 75 degrees, you would expect it to create a wave that looks like that in lead 2, because lead 2 is 60 degrees. Wave of depolarization between 0 to 75 would be moving towards it, and hence the positive deflection. On the other hand, if you were to look at AVR, notice that 0 to 75 degrees is actually traveling opposite to AVR. So you would see a negative deflection. And if you were to look at lead V1, so V1 would be right about perpendicular to the direction of flow of the atrial depolarization wave. So in essence, what's happening is the wave of depolarization is going perpendicular to lead V1. And so you would expect to see a biphasic wave. Now, eventually, when the wave arrives at the AV node, as we've talked about, it slows down. The purpose of the slowdown is to allow for the atria to finish contracting, and that way blood flows from the atria to the ventricles before the ventricles are able to contract once they're stimulated. So, because of the slowdown at the AV node, you would see a flat line, and following that, the wave travels through the bundle of His, and then it goes through the septal fasciculus, and here the wave of depolarization goes to the interventricular septum, which depolarizes from the left. So this would be the left to the right. So this would be the right. So notice how the wave of depolarization is going from the left to the right. So if you think about it, we mentioned that 1 and AVL are facing towards the lateral side and they're leftward facing. So you would expect, well, let's go ahead and draw this out again. So you have the P wave and then a flat line. And then because the septum is getting depolarized from the left to the right, and 1 and AVL are facing to the left, you would expect a small negative deflection, and this would be seen in leads that face towards the left. Now, once the septum is depolarized, the right ventricle and the left ventricle all depolarize. Now, the thing is, you have multiple vectors going in every direction. But the thing is, the left ventricle is much more bulkier compared to the right ventricle. And so there are more waves of depolarization going to the left. And if you were to think about it, the vector would look something like so, between minus 30 degrees and positive 90 degrees. So because of this very heavy, bulky wave of depolarization going there, you would see a positive deflection. And sometimes this may be followed by another negative deflection. And once the depolarization is complete, you would have a return of the flat line. Now, once that's done, because all the cells in the ventricles are depolarized, they would eventually repolarize. So you would have another wave like so. And this represents ventricular repolarization. We said this one is ventricular depolarization, and this one is atrial depolarization. Now, a couple of quick questions. What happened to the wave of atrial repolarization? Well, because the atria is not as big as the ventricle, the atria repolarize at the time the QRS complex is happening, and so the QRS complex hides off the wave of atrial repolarization. Another question that comes up is, if ventricular depolarization represented by this and ventricular repolarization represented by this are opposite phenomenon, why are both of those looking positive? The reason is that, as a general dictum, the cells that depolarize the last are usually the first to repolarize. So depolarization and repolarization travel in opposite directions, and so you notice that both of them appear positive. So they're positive because they're really happening in two opposite directions. Now, we mentioned how for looking at the P wave to know the direction of atrial depolarization, ideally you should be looking at leads to AVR and V1. Now, let's go ahead and take a deeper dive into how we can assess ventricular depolarization. So for the purpose of this exercise, you would want to start looking at three leads. So you want to look at lead 1, lead 2, and AVF. So you're looking at lead 1, lead 2, and AVF. Now there are 8 possible scenarios, right? So you have 2 part 3 scenarios that can happen based on all the different permutations and combinations. Let's draw them out. So positive, 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 negative, positive, negative, positive, positive, negative, 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 positive, positive, negative, positive, negative, 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 positive, negative, negative, negative. So this is pretty much every combination there is. So let's see what each of these mean. Now, if we were to take the first scenario, let's do an additional thing. So for lead 2, if you imagine a line that's perpendicular to it, it would look like so. So any wave that's flowing towards lead 2 would kind of fall in this general direction, otherwise it would be facing away. So if you look at lead 1 is positive. So that means the axis of the QRS would be somewhere here. Lead 2 is positive, so the axis of QRS would be somewhere here. And AVF is positive, so the axis of QRS would be somewhere here. So based on all this, notice that the area of overlap is this specific area. So the axis would be the area of overlap of all 3 zones, And so the axis in this case would be 0 to 90 degrees, and that's normal. Now let's take the second example. So we said 1 is positive, 2 is positive, and AVF is negative. So now let's go ahead and draw the axis again. So you have 1, AVF, and 2. So given that 1 is positive, you would expect the wave of depolarization to be somewhere here. We also said 2 is positive, so let's draw the line perpendicular to 2. And now we would expect the wave of depolarization to be somewhere here. And lastly, we said AVF is negative, so we would expect the wave of depolarization to be going away from AVF, so it would be somewhere here. So now, notice that the area of overlap is this box right here. So this is where all three lines are overlapping. And because lead 2 is at 60 degrees to lead 1, this must be minus 30, right? So if you think through it, the axis in this case would be 0 to minus 30 degrees. And this is also considered normal. Now, let's go ahead with the third example. So let's go ahead and redraw the leads. You have lead 1, lead AVF, and lead 2. Alright, so here we're saying 1 is positive, so it must be somewhere here. Then we're saying 2 is negative, so let's go ahead and draw the line perpendicular to 2. And now you know that it's somewhere here. And then we said AVF is positive, so it must be somewhere here. Notice how there is actually no overlap of all three zones, so this is not possible. This permutation and combination is not possible, and if you see this, something is wrong with the way the EKG was done. So physiologically, as well as by the laws of physics, this is just not possible with the conventions we've adopted. So now let's look at the fourth scenario. So we'll go ahead and label the axis. All right, we said 1 is positive, so that would mean it's somewhere here. Then we've said 2 is negative, so again, let's draw the imaginary line perpendicular to 2, and 2 is negative, which means it's somewhere there. And then we said AVF is also negative, so it means it's somewhere here. So the area of overlap is right here. So we already said that this is negative 30 degrees and this is 90 degrees negative. So in this case, the axis is between negative 30 to negative 90. And when the axis falls in this area, this would be considered left axis deviation. So let me go ahead and erase these pictures and make some space, and we'll resume. So let's go ahead and draw our vectors again. So you have lead 1, lead 2, and AVF. And we've noticed that 1 is negative, 2 is positive, and AVF is positive. So 1 is negative, and 2 is positive. So again, let's draw the line perpendicular to 2. So 2 is positive, so it means it's somewhere here. AVF is also positive, so it must be somewhere here. And if you look at it carefully, you would see that the area of overlap is this zone right here. So then the axis would be between, well, this is 90 degrees. And because this is perpendicular to lead 2, it would be 60 degrees plus 90 degrees. It's going to be 150 degrees. And so the axis is between 90 to 150 degrees. And this would be right axis deviation. So let's go ahead and draw out the next scenario. One, two, AVF. 1 is negative, so it must be somewhere here. 2 is positive, so we draw the perpendicular line and 2 goes this way. And AVF is negative, so it goes like so. Now, notice again that there is no overlap, and so this scenario is not possible. Now, let's take up the next scenario. So you have leads 1, 2, AVF. So we said lead 1 is negative, so it's somewhere here. Lead 2 is negative. So let's have our imaginary line perpendicular to lead 2, and 2 is negative, so it's somewhere here. And AVF is positive, so it's somewhere here. And so the axis is somewhere right here. Now, we already said this is 150 degrees and this is 180 degrees. So in essence, the axis now is 150 to 180, and this would be considered right axis deviation. Now let's get the last scenario, and then we've mastered how to interpret a ventricular depolarization axis. So we have leads 1, 2, AVF, and we've said 1 is negative, so it's somewhere here. We've also said 2 is negative, so we have the imaginary line, and we said 2 is negative. And lastly, AVF is also negative, so that would go somewhere here. So notice how the overlap area is like so. So in essence, it's between negative 90 to 180, and this would be considered extreme right axis deviation. So we've thought through the process of how different waves look, but if you had to communicate it to someone, you would want to call the waves something. So let's go ahead and see how we could name the waves. So the waves in an EKG would typically look something as follows. And sometimes you can have an additional wave, so we'll just put it in a different color. So the first wave we're seeing would be called the P wave. And as we talked about, this represents atrial depolarization. Following this, we said that there is this flat line because there is slowdown in the AV node. And after this, you see this complex. The complex is called the QRS complex, but then it can take up one of several shapes. Let's look at the permutations and combinations. So anytime the first wave is a negative deflection, it's going to be called the Q wave. Anytime you see a positive deflection, it's the R wave. And again, here this would be the Q, this would be the R, and the negative deflection that follows an R wave is the S wave. Now here there's just a positive deflection, so that's an R wave. Here there's a negative deflection, but there is no positive deflection, and this would be called the QS. And here, notice how you see a first upward deflection. So that's a R. The negative deflection would then be an S. And you have a second deflection, and you've already used up R. So we're going to call this R prime. So this would be the RS R prime pattern. And here you have a positive deflection. So this is going to be an R. And then you see a negative deflection, and this is an S. Notice how you would not call this the Q wave. And the reason for that is that the initial deflection is not negative. So, well, that's the QRS complex. And as we've discussed, this would signify ventricular depolarization. And then you would see the flat line again. And after this, you would see another wave. And this wave is the T wave. And this signifies ventricular repolarization. Now, sometimes you may see an additional wave, and that would be called the U wave. So you have the P wave that represents atrial depolarization, the QRS complex, which represents ventricular depolarization, and the T wave, which represents ventricular repolarization. Now, as we've talked about previously, atrial depolarization is hidden within the QRS complex, and the QRS and T waves are usually in the same direction because depolarization and repolarization happen in opposite directions. All right, very good. Now, let's also go ahead and look at a few other things. In an EKG, when you're referring to a segment, it's a straight line. And when you're referring to an interval, it usually includes at least one wave. So when we refer to, let's go ahead and draw this back. So P, QR, S, and T. So the PR interval would be like so. So it's from the start of the P wave to the beginning of QRS. So this is the PR interval. And it's essentially from the beginning of atrial depolarization to the beginning of ventricular depolarization. The segment from the end of atrial depolarization to the beginning of ventricular depolarization, this one, it's going to be called the PR segment. We've already talked about the QRS, which is ventricular depolarization. Now, the segment between the QRS and T wave, so between ventricular depolarization and ventricular repolarization, would be the ST segment. And the interval between the beginning of ventricular depolarization to the end of ventricular repolarization would be the QT interval. Now, this lays a basic foundation of what to think about when you're looking at an EKG. And in the next video, we'll look at the paper on which an EKG gets transcribed and how a normal EKG looks like. Thank you for watching.